Let's take a look at this problem concerning the graph of a cumulative distribution function. The top picture here shows the probability density histogram of the random variable x. We will look at the random variable m later on. Let's figure out the value of f of 2. Now recall that the cumulative distribution function f of 2 is the probability that the random variable x is less than or equal to 2. That's the definition of a cumulative distribution function. How can x be less than or equal to 2? Well, there's two ways that can happen. Either x can be equal to 1 or x can be equal to 2. Those are the two ways that the random variable x can be less than or equal to 2. And in our case, that would be 1/6 plus 1/6 for 2/6, 1/3. For part 2, f of 4.5. So f of 4.5 is the probability that x is less than or equal to 4.5. And there's only 4 ways that can happen. X can be equal to 1, or it could be equal to 2, or it could be equal to 3, or it could be equal to 4. There's 4 ways that x can be less than or equal to 4.5. So the 0.5 is almost a red herring in this problem. The 4 possibilities are x equals 1, 2, 3, 4. So that's going to be 4 times a sixth, 1/6 plus a sixth times a, plus a 6 plus a sixth, which is 2/3. F of negative 1. Well, that's the probability that x is less than or equal to negative 1. And of course, that is impossible. X has to be either 1, 2, 3, 4, 5, or 6. And so there's no way for x to be less than or equal to negative 1, so the probability of that happening is 0. And finally, f of 7. That's the probability that x is less than or equal to 7, and that is guaranteed. The possible values of x are 1, 2, 3, 4, 5, and 6, and so all of those are less than or equal to 7, and so the chance that x is less than or equal to 7 is exactly 1. Part 5, let's draw the graph. Okay, so let's do that down here, and let me try to carefully draw this. So there's 1, 2, 3, 4, 5, 6, and over here 1/6, 2/6, 3/6, 4/6, 5/6, and 6/6, which is 1. So here's 1, 1, 2, 3, 4, 5, 6. Okay, now let me start carefully drawing in the graph of this. We saw that f of 2 is equal to 2/6, so that's here. And similarly, f of 1 is 1/6, f of 3 will be 3/6, f of 4 is 4/6, f of 5 is 5/6, f of 6 will be 6/6, which is 1. If I plug in anything that's bigger than 6, I get 1 automatically, so it's going to be graphically flat on this side. If I plug in anything that's less than 1, the probability of that happening is 0. But as soon as I get to 1, I jump. So I've got a hole in the graph at 1, and I have a jump here. Now we saw at 4.5 that f of 4.5 is also equal to 4/6. And likewise, same for f of 4.1, 4.9, as long as I'm not equal to 5. So I've got a graph that goes like this with a hole down here. Now hopefully you can kind of see what's supposed to happen, that the graph of the CDF is going to go this kind of step function that's increasing, or at least non-decreasing. So you might have places where it's flat, but the function never decreases. So the places where the graph goes down, that's just simply me not drawing carefully enough with the mouse. We have a flat function or increasing, but a function that never decreases. And the y-coordinates must be between 0 and 1 because probabilities must be between 0 and 1. So that's the graph of f of x. Let's now turn to the graph of the CDF for m. And we can do that similarly. It's actually a little bit easier because there's only two values to worry about. So here's the y-axis, and here's the x-axis. So there's two x values to worry about, -1 on this side and 4 on this side. And again, let me count off 1/6, 2/6, 3/6, 4/6, 5/6, and 1 for 6/6. Now, as before, if you're greater than or equal to 4, the probability is less than or equal is 1. And if you're less than -1, the probability is 0. So we have a graph that looks like this, which parallels what we did over here for the CDF of x. At -1, the probability that x is equal to -1 is 5/6. And so we can jump all the way up here to 5/6 for the probability. So the probability that m is less than or equal to -1 is 5/6. And that continues flat here until I get to 4. And then the graph jumps there. So once again, for a discrete random variable, the graph of a CDF is kind of the stair-step function that increases, or at least is non-decreasing.